is clear to you? Because of the way the algorithm is designed, we can actually have difficulties in navigating certain areas in the state space. So what this diagram represent is, it represents two axes. One axis is state space, horizontal axis, and the vertical axis is objective function. So we are actually looking at in the state, the whole state space with respect to these two dimensions. So any two nodes in this diagram that you're looking at, any two nodes I pick up in this any two, sorry, points I pick up along the x-axis would represent two different states of the environment and the corresponding objective function value for those states. Okay. Now, due to the nature of the algorithm and the way it is described, these particular thing is called as state space. I'm not having that word on my tongue, but it's a state space landscape. Yeah, this is called a state space landscape because it's we are referring it to as hill climbing, or we are climbing a region. So that's why this landscape word come into picture. So this is called as a state space landscape. In this landscape, we can select certain regions and try and understand how our hill climbing algorithm would behave if we were at that particular spot. As it sees over here, this particular, if I were at this particular position on the state space landscape, okay, so this position means my current state is over here and the objective function value is this one. Okay, the objective function value can be traced it to this particular value. Now, if this is the place where I am, who are my neighbors? So neighbors would be the node which are adjacent to me. So I may, if I discretize this diagram, I may have one neighbor situated over here and another neighbor situated over here. So we are just actually hoping that if this could have been a two-dimensional diagram and we could discretize it based on certain parameter, this narrow region would involve or would actually show all the neighborhood cells of the current node. Okay, and you imagine that the tree that we have something of this sort. Say suppose this node which we are pinpointing as current node right now is looking like this, and possibly there are 4 child nodes to this current node, and those 4 nodes are maybe one is this, another one is this, another one is this, and another one is this. So there are 4 states which are the child node states that we would be comparing which one of them has the best possible value. Okay, so these 4 actually will sit into this narrow region somewhere. Okay, so this may have least value of objective function, so it will sit over here. Okay, this may have higher objective function value maybe, so it may sit over here maybe, and something like that. So all 4 nodes, all these 4 nodes are actually going to sit into this narrow region. Okay, this narrow region जो yellow vertical line से मैंने दिखाया है उस region में वो रहेंगे. And what my algorithm is going to do now is it is going to pick up the best possible. Say suppose this is the best possible, and we then compare if that node is represented by say red. So this is the best possible value of my objective function of my child nodes. Then out of the 4, I pick this up, and then I compare the current node which is in yellow with this with respect to the objective function value, and I clearly see that the objective function value for this node is better. So I concede my spot yellow to this guy. So now the yellow dot would move itself to this spot on the graph. Okay, its color is still red. I don't tend to use colors, but this blackboard is giving me so itching to use colors. उल्टा वो confusing हो जाता है ज़्यादा. So what the algorithm is doing is something like this. Now in this region, in the whole landscape, if I were anywhere on this curve, which is a increasing slope curve, I will always be able to navigate it and reach to a point where I reach this point. Now from this point, will I be able to move anywhere? Let us check. So what will we do is, we'll do again the same thing. We will discretize this curve around this point, and when we discretize this curve around this point, again we'll have a small region of nodes like this. This time I'm drawing them with red, and all the nodes in this narrow region. So this is where all the nodes are situated, and this curve is representing the objective function value for all the nodes in this region. You can visually also inspect and understand that the local maxima node, the pointed node, yellow pointed node, is going to have higher objective function value than any of the other nodes. So basically, my algorithm can't move from this algorithm ahead in that loop. It will just get out of the loop and my algorithm will halt. So this will happen at every local maxima. If you luckily happen to start your search from, say, this spot, the local maxima here is actually the global maxima, and you will reach the global maximum node. That's for sure. Okay, so that is what we are learning by looking at this landscape, state space landscape. The other important thing that we discussed last week also, I'm again discussing this because it is very important to know, is called as a shoulder. So shoulder is a region which is a flat region in the state space landscape. That is, in that particular region, every other node in the neighborhood will have exactly the same value of objective function on one direction, and on the other direction I have all the nodes which are having value less than me. I have all the nodes where objective function values are less than me. So if I want to actually enact a example as a state space example of a shoulder, then maybe I can draw it like this. I can say that, okay, I may have a state space with one node having objective function value 8, which is current node, and there are other nodes in its vicinity or its child node. They are all 8. They're all 8. And if any node has a least value, that is any node has other than 8 value, that is going to be a smaller value. Okay, so this particular thing that you are looking at is a kind of a plateau, not plateau, sorry, is a kind of shoulder. One node has value lesser than for the objective function, one node has the value less than the current node, and all the other successors have exactly same value for objective function as that of the current node. Now, as our algorithm suggested, what we are supposed to do when we are expanding this, find out the highest valued node. So it is 8. You may pick up any one between these three, but it will remain 8. Now, when you compare this 8 with the 8 that you have, since both the values are same, what will happen? I will just can't swap it, right? It is same as that of the current node. Okay, this is just one step I am saying. So shoulder में आगे आप देखोगे तो इसके आगे जाओगे तो भी आपको सेम रीजन दिखेगा, तो इसके चाइल्ड नोड भी 8 ही है. Now even if, so somebody may say that, okay, still sir swap ना, 8 है तो ये 8 तो वर्स नहीं है, why not just swap it, fine. But then probably the chance is that if it is a shoulder, even the next step, one extra step, so this may actually be the region, and I selected this node on the edge of it, and still if I see ahead, I have all the nodes having value 8. So all the subsequent nodes, the siblings of this level, as well as the next level nodes, they have value 8. So this is how we can describe how a shoulder would look like on a state space, and this is how it can be visualized on a two-dimensional graph. Okay, so that's the shoulder. So shoulder is also a very difficult region in the state space landscape to navigate. Which is the easiest region to navigate? The easiest region to navigate on the state space curve for hill climbing problem is where the curve is increasing slope, has an increasing slope. Okay, that I can always navigate. But when the curve slope changes, so this local maxima में क्या होता है, slope positive है वो negative हो जाता है. So here the slope of this curve जो increasing था वो decreasing हो गया. Okay, so that is how we can think of a local maxima, a point in the state space landscape where the slope changes its sign. That's the local maxima, because maxima पे वो tangent निकाल सकते हो आप, right? So it's a flat zero value for the slope. Okay, if this local maxima extend to a region rather than a point, then this local maxima will be called as a plateau. This is, I guess, the last thing that we had discussed last lecture. Okay, so these are certain issues with hill climbing algorithm that the hill climbing algorithm is not well equipped to in its nascent version to handle. उसका जो nascent version है, उसका जो play version है hill climbing algorithm का, तो ये typical regions है state space landscape में जिसको navigate करना मुश्किल होगा for a hill climbing algorithm, and you need to actually modify the existing way of representation of this algorithm if you want to navigate these landscapes. Okay, so which are the landscape? Number one is the local maximum, number two is any shoulder, and number three is plateau. Okay, ultimately for any search algorithm the goal should be to be able to get to the global maximum. That's the whole idea in search algorithm. I want to satisfy as many criteria as possible, but please understand the reality of the situation, that many a times even the suboptimal goals might be reasonable goals if the state space itself is so huge that navigating to global maximum may be almost impossible because of the amount of searches that we need ultimately to reach the global maximum. Okay, so that's why sometimes it may be okay for certain problems, even if you get the local maxima, it's okay. And such problems in real world are majorly the problems related to cognitive intelligence, like uh, identifying an object in an image, getting to hear and understand voice of a human or any animal for that instance, and identification from the voice, identification of a person, maybe iris detection, maybe the identification of your biometric data. All these things actually require some sort of cognitive intelligence into our algorithms, and such places the complexity of the problem is so much so that getting to the global maximum might not be the thing that we want, and we can do away with reaching even the local maximum, and that's where it is reasonable to use hill climbing search